In this topic, we'll lay the groundwork for everything that follows. You'll see what modern cryptography actually does, how symmetric and asymmetric keys differ, and how hashes, MACs, and digital signatures combine to deliver real security properties for your systems. When we talk about security in this course, we're really protecting four things. Confidentiality means only the right people can see the data. Integrity means data can't be changed without us noticing. Authenticity is about knowing who we're actually talking to. And non-repudiation ensures someone can't later deny an action they performed. Everything else in this course builds on these four goals. Symmetric cryptography is the high-speed workhorse of modern security. One secret key is used for both encryption and decryption, which makes it extremely fast and efficient for large volumes of data. That's why it underpins VPNs, storage encryption, and many application protocols. The main challenge isn't performance. It's safely getting that shared key to every system that needs it. Asymmetric cryptography tackles that key distribution problem by splitting one secret into two related keys. The public key lives in the everywhere zone. You can publish it, send it over email, even put it on a website. Anyone can use it to encrypt data or verify signatures. The private key lives in the vault zone. It never leaves secure storage. Only that private key can decrypt or create valid signatures, which is why protecting it is absolutely critical. Symmetric and asymmetric crypto solve different problems and are usually used together. Symmetric algorithms are extremely fast, so we use them for bulk data like disk or VPN encryption. But both sides must already share the same secret key, which creates a deployment headache. Asymmetric crypto is slower and more CPU intensive, but it lets you publish a public key widely and keep a private key protected. That makes it ideal for TLS handshakes, certificate-based identity, and digital signatures. A cryptographic hash is like a digital fingerprint for any piece of data. You feed in a file, a message, or a password, and you get a short, fixed-length output. It's a one-way transformation. From the fingerprint, you can't recover the original data. Good hash functions are collision-resistant, meaning it's extremely hard to find two different inputs with the same fingerprint. You can use that fingerprint idea to detect tampering. Run a file through a hash function once, store that short output, and forget about the full content. Later, hash the file again and compare. If even one bit changed, the hash output is completely different, so you instantly know it was modified. This is how software downloads, logs, and even some blockchain systems detect tampering. Just remember, hashes prove integrity, not who made the change. Hashes alone only tell you if data changed. They don't tell you who created it. HMAC fixes that by combining a cryptographic hash with a secret key that only the sender and receiver know. If the HMAC verifies, you know the data is intact and that someone who knew the shared secret produced it. That gives you integrity plus authenticity in a single primitive. Digital signatures answer a key question. Did this really come from who it claims, and was it unchanged? We first hash the data, then use the sender's private key to sign that hash. The result is a compact digital fingerprint, cryptographically bound to the sender. Anyone with the corresponding public key can verify the signature without ever sharing a secret. Non-repudiation is where cryptography and law shake hands. It's about being able to prove that a specific person took a specific action at a specific time, and making that proof stand up to challenge. With strong digital signatures, solid identity checks, and trusted timestamps, the signer can't later claim, "That wasn't me," or "I never approved this." PKE is how we turn raw public keys into something we can actually trust at scale. At the top, a root CA is trusted a bit, like a country's passport authority. It delegates to intermediate CAs, which handle day-to-day issuance and can be replaced if compromised. Those intermediates issue leaf certificates to servers, services, or users. When your browser validates a site, it's really walking this chain, asking, was this key ultimately vouched for by a trusted root? EDIS gives you a three-step ladder of trust for digital signatures. At the bottom is a basic electronic signature, almost anything that links a person to data, but with weak guarantees. Advanced electronic signatures add strong identity binding and integrity checks, so you can detect tampering and reliably know who signed. Qualified electronic signatures go further. Keys are held in a certified device under a supervised provider. Only at this top level does the signature gain full legal equivalence to a handwritten signature across the EU. HTTPS shows how these building blocks work together in practice. First, the browser uses asymmetric cryptography and the server's certificate to authenticate the server and agree on a shared symmetric key. Once that key is in place, it protects all bulk data so outsiders only see ciphertext. Finally, hashes or MACs ride along with each message, so the client and server can detect any tampering and be confident about who actually sent the data. Let's tie this together. Symmetric and asymmetric keys are complementary. One gives speed, the other safe distribution and signatures. Hashes and HMACs power integrity and authenticity. PKI binds public keys to real-world identity, and EDAS with qualified trust services provides the legal framework that turns all this crypto into recognized digital trust.